Hello everyone, my name is Jyoti Sarvade and today we are going to learn about autoencoders. So this is the content we are going to see in today's presentation. First of all, let's see what is autoencoders. Autoencoders are special types of neural networks used for unsupervised learning. Their main job is to understand patterns in data and represent it in a smaller, more manageable way. They do this by learning from input data without needing labels or guidance. Think of autoencoders as detectives trying to uncover hidden relationships in the data. The process they follow is like a game of telephone. First, the input data is passed through the encoder network, which squeezes or compresses it. Then, this compressed version is sent to the decoder network. The decoder's job is to reconstruct original input based on the compressed version it received. It's like taking a secret message, encoding it into simpler form, and then decoding it back to its original form. So, there are three parts of autoencoders. First is encoder. The encoder is like a scanner at the beginning of the journey. It takes the input data, which could be anything from text, images to text, and then compresses it. This compression is like shrinking a big balloon into a smaller one, making it easier to handle. The encoder's job is to capture the essential features of the input and represent them in a lower dimensional form. It's like taking a big puzzle and considering it into just few pieces that still capture the main picture. Next is bottleneck. Think of the bottleneck as narrowest part of the funnel. It's a special hidden layer within the autoencoder where the magic happens. This layer has fewer nodes compared to the layers before and after it. The number of nodes in the bottleneck layer determines the dimension of the encoding. Imagine you are pouring sand through a funnel and it's getting compacted into a smaller space. That's what happens in the bottleneck layer. So next part of the autoencoder is decoder. The decoder is like a magician assistant who knows how to bring things back to life. It takes the compressed representation from the bottleneck and reconstructs the original input. This reconstruction process is like unfolding the compressed balloon back to its original size. The decoder's job is to decode the compressed information and recreate input as accurately as possible. It's similar to putting together the pieces of puzzle to reveal the full picture once again. So next, balancing depth and dimensionality. Autoencoders have a tricky job. They need to find the right balance between how deep they dive into the data and how much they simplify it. Pictures it like this: if autoencoders goes too deep and makes the bottleneck layer too large, it might end up trying to memorize every little detail of the input. This can lead to overfitting, where the model gets too good at remembering the examples it's seen but struggles with new ones. On the other hand, if the bottleneck layer is too small, it might miss out on capturing important relationship in the data. It's like trying to describe a whole picture with just few words. You might miss some crucial details. Unlike other methods like principal component analysis (PCA), which take a linear approach to dimensionality reduction, autoencoders are like detectives who can beyond straight lines. They can capture non-linear patterns and correlations in the data, which makes them more powerful in cases where linear methods fall short. So next, types of the autoencoders. First type of the autoencoder is undercomplete autoencoder. Undercomplete autoencoders are like strict teachers who don't let you use cheat sheets. They impose strict limits on how much information can pass through. Picture it this way: imagine a funnel that's narrower at the bottom than at the top. That's how the hidden layer and the bottleneck node counts are constrained in undercomplete autoencoders. This restriction ensures that only the most of important information gets through. By limiting the flow of information, under-complete autoencoders prevent the model from memorizing the input data. This is important because we want the encoding to capture meaningful patterns rather than just regurgitating what is seen before. The goal is to reconstruct the input data as accurately as possible while still keeping the encoding concise and meaningful. It's like trying to summarize a long book into a short paragraph. You want to capture the essence without getting bogged down in every detail. So next type of the autoencoder is sparse autoencoder. Sparse autoencoders act like smart gatekeepers, making sure that only the most important information gets through without letting any unnecessary details sneak in. Imagine a gate with tiny holes that only allow specific things to pass through. Similarly, sparse autoencoders regulate the activations between hidden layers, making sure that each node contributes meaningful information without just memorizing the input. This helps to prevent overfitting, where the model becomes too good at the remembering the example it's seen but struggles with the new ones. Instead of sparse autoencoders, focus on capturing the essential patterns in the data without getting distracted by noise or irrelevant details. Think of it as a filter that sieves out important grains from a pile of sand, ensuring that only the most valuable information remains. So next part on the autoencoder is denoising autoencoders. So denoising autoencoders are like expert cleaners who focus only on the important parts of the image, ignoring any messy distractions. If you have ever tried to clean up a photo by removing background noise, denoising autoencoders do something similar. They zoom in on the main objects in the image and filter out any unnecessary noise or clutter. Unlike other types of autoencoders that compress the input data, denoising autoencoders work on cleaning up the input, creating a more polished version without the need for strict node restriction or regularizers. This is possible because denoising autoencoders have unique way of understanding the input-output dynamics. They focus solely on representing the objects in the image, making sure they stand out clearly without distractions. It's like having a magic eraser that removes all the scribbles and marks from a picture, leaving behind only the essential elements. Next type of the autoencoders is contractive autoencoders. So contractive autoencoders are like attentive note takers who ensure that similar inputs lead to the similar notes. Just like how denoising encoders clean up noisy images to aid feature extraction. Imagine you are taking notes in class and you want to make sure you capture the main ideas accurately. Contractive autoencoders do something similar. They focus on extracting the essential features from the input data while ensuring that similar inputs produces similar encoded representation. Autoencoders are like versatile tools that can handle different types of data. For images, they use convolutional neural networks, while for time series data, they employ recurrent neural networks. Next type of the autoencoders is variational autoencoders. Variational autoencoders are like artists who paint a simplified yet meaningful version of a complex picture. They take complex data like images and condense the essential information into a compact representation. This representation makes it easier to reconstruct the original data through a decoder. Think of the encoding as a sort of treasure map where each feature represents something important about the data, like a person's smile or their skin tone. Together, these features form the latent space, which defines the key attribute of the data. So there are some applications of the autoencoder. First application of the autoencoder is autoencoders are like detectives that can uncover unusual patterns in the data, making them incredibly useful for anomaly detection. They can spot deviations from normal behavior, like fraudulent transactions or unusual patterns in medical data. Just like how you might use a noise cancelling app to remove background noise from a recording. Hmm. Just Autoencoders are great at noise removal. They can clean up noisy images, audio recordings, or any other type of the data by focusing on the essential features and filtering out the unwanted noise. Autoencoders also have creative side. They can act as generative models. This means that they can generate new data samples that resemble the one they were trained on. It's like having an artist who can create a new painting based on the style they have seen before. Another interesting application is collaborative filtering, where autoencoders can help recommend products or content to users based on their past preference or behaviors. They learn from the interaction between users and items to make personalized recommendations, like suggesting movies on a streaming platform or products on an e-commerce site. So, in conclusion, autoencoders are like skilled architects that simplifies complex structure and extract the most important features, ensuring that vital data information is preserved. The hidden latent feature they capture encapsulate the essence of the data, empowering a wide range of applications across machine learning and AI. From enhancing images to analyzing time series data, autoencoders play a crucial role in various fields, making tasks more efficient and effective. Thank you.